Hello there. I'm Dr. Joseph, and today we're going to be differentiating parametric equations. So last time we introduced what these are. It's a way to have a little object running around the plane. And we are going to now see how to find dy dx. So that's actually like you have some crazy curve, and we're not concerned anymore with whether or not y is a function of x, but we still may want to know at a point what is the slope of the tangent line, right? And so that's what dy dx is. And also the second derivative of y with respect to x. And if you remember Calc 1, that tells us about concavity, curvature, that sort of thing. So that's our goal for today. And let's see, very important to be looking at what is the variable we're talking about when we're talking about derivatives, because now there are a few floating around. Okay, so how do we do this? Okay, so here's the chain rule, thinking of x as a function of t and y as a function of x, f of x. So y is f of x is x of t. So f of x of t is a composition, and we can apply the chain rule. So you see that chain rule happening right there, very important. And that means if we solve for dy dx, we get dy dt over dx dt. So this is the way that we often write the chain rule. But in this case, I'm going to write it out with this other notation to try to make this clear. So this first term is dy dx, derivative of f or y with respect to x. Then the second term is derivative of x with respect to t. And this way of writing it makes the chain rule look like we're just canceling the fraction, right? Because the chain rule says this is equal to dy dt. Okay, and then what we are doing to get this final formula is just solving for dy dx, right? So you just divide both sides by dx dt, and that's how you get this formula. So let's see how to use that. So here our parametric equations are that x is 5 minus t cubed and y is t squared plus 3. And it says find dy dx when t is equal to 4. Again, from Calc 1, you should know you need to find dy dx as a function before you go plugging anything in. And what our formula says is that dy dx is dy dt over dx dt. Okay, so this one isn't so bad. dx dt is negative 3t squared, and dy dt is 2 times t. So we just have to divide 2t over negative 3t squared, and that's negative 2 over 3t. So that's dy dx for any value of t. And now to answer the question, dy dx, this bar means evaluated when t is equal to 4. I just plug in 4. Negative 2 over 3 times 4, which is negative 1/6. Okay, so not too bad. Here's where it gets a little bit hairier. Taking the second derivative of y with respect to x from the parametric equations. So second derivative of y with respect to x is the derivative of the derivative. And the way that I like to explain this is what we learned on the last slide was that dy dx is equal to dy dt dx dt. And this is true for any differentiable function y. So the kind of sneaky way to get this is that you plug in y prime for y on both sides of this equation, and that gives you dy prime dx equals dy prime dt divided by dx dt. So it's the same formula as before, but we're just plugging in y prime instead of y. And of course, dy prime dx is the second derivative of y with respect to x. And dy prime dt is what you see written here, the derivative with respect to t of dy dx, because remember, that's a function of t, divided by dx dt. Okay, so that's a lot of words. Let's do an example. Oh, good. It's the same example from before. So let's just remind ourselves dx dt was minus 3t squared. Dy dt is 2t. And dy dx is 2t over minus 3t squared, which is minus 2 over 3t. That's dy dx. Now, second derivative, we're going to reuse quite a bit of that information because we're going to take derivative with respect to t of dy dx and do all that over dx dt. Okay, so I already know dx dt from the first time around. That's negative 3t squared. And then separately, we need derivative with respect to t of dy dx. So dy dx was negative 2/3 t inverse. I'm writing it that way because I want to use the power rule. So the power rule tells me I get 2/3 t to the negative 2, which is also 2 over 3t squared. Okay, so coming to the end, we've got 2 over 3t squared over negative 3t squared. So in total, that's negative 2 over 9t to the fourth. So that's the second derivative for any value of t. And now d squared y dx squared evaluated exactly when t is equal to 4 is negative 2 over 9 times 2 to the fourth, which we could leave that like that, but I'm going to use this trick again that 9 times 9 times 3 times 3 times 4 times 4 is 12 times 12. So that's negative 2 over 144, which is negative 1 over 72. So notice, so why do we care? What does this mean? Notice, like, no matter what t is, this is negative, right? Because t to the fourth is greater than or equal to 0. So let's look at the graph real quick. Here's the graph, and you can see, except at this one point where dy dx does not exist, this is concave down. So we knew that because the second derivative was negative, going back to Calc 1. And I graphed it with the little slider, and when t is exactly 4, that's the point we're at, and we know it's concave down there. So that's the sort of thing you can look at and figure out about the graph knowing the second derivative. Um, Back to slides. So here's an example you can try where y is natural log of t and x is t squared plus t. Find dy dx first, and then you will use that as you find the second derivative. Um, be careful, there's some chain rule in this problem. I'm going to show the answer. And there you have it. All right. Have a good day.